21 from the Barons. If f is a differentiable function such that f of 3 is 5, so we've got a point there, and f prime of 3 is negative 0.4, we've got a slope, then f of 3.1 is approximately, well, we've got a lot of options right around 5 as far as just looking at our choices. So what can we do with this point and this slope? Well, if we know a point and we know a slope, we can write an equation of a line. And in this case, it'd be the equation of a tangent line because we've got the slope at a point. So y equals mx minus x plus y. So we got our slope-intercept form there, our point-slope form. And then what that allows us to do is we can approximate some values around our tangent line, and 3.1 is definitely very close to 3, so we can approximate it. Y equals negative 0.4, 3.1 minus 3 plus 5. 3.1 minus 3 is 0.1 times 0.4 is negative 0.04, so negative 0.04 plus 5 would be 4 100ths less than 5. Should be 496. Now, a quick discussion. The next question sometimes either in a free response or maybe even in multiple choice would be, is it an over or an under approximation? And we couldn't tell on this because we don't know what the function was and we don't know about the value of the second derivative. But we would look at the value of the second derivative and we'd say, is it greater than 0? Is it less than 0? And what that means is if the function is concave up, meaning the second derivative is greater than 0, the tangent line approximation would always be an under approximation. And similarly, if it is concave down, the tangent line would always be an over approximation. Now that's not in this problem, but it's a very good thing to talk about in review. All right, number 22. A particle moves along the y-axis with its position at time t given by h of t, where a and b are constants and they're not equal. For which of the following values of t is the particle at rest? So if we know a position function to be at rest, its velocity would be 0. So we can derive and set it equal to 0. So the derivative of h is actually really not bad. We've got a product rule going on. The derivative of t minus a is just 1. The derivative of t minus b is just 1. So really we've just got the negative in front of, let's do the first bow tie here, times that 1 minus the derivative of the first times the second. Very easy product rule there. I would think the only mistake maybe would be with that minus sign. It's got a little touchy there. Set that equal to 0. So let's distribute. Negative t plus a minus t plus b. Negative t plus negative t is negative 2t. Subtract the a and the b over. Divide by the negative 2. T equals, the negatives go away, a plus b over 2. Good work. 23 is kind of our classic graph and integral problem. The graph of a differentiable function f is shown. If h of x equals the integral of that from 0 to x, which of the following is true? And you know, they do that thing of like which is false, which is true. Very good reading problem too. So if h of x is this, and we're talking about h prime and h double prime, so obviously we kind of want to derive those things. So what is h prime? H prime, according to our fundamental theorem of calculus, is just going to put the x in. So that's just going to be f of x. The integral of f of t would be big F. If I derive that, I'm going to get back to little f. So that's where that comes from. H prime is going to be the derivative of that. Good. So really, this is a graph of f. And they're saying that is h prime, so we got to think about this as a graph of our derivative. So now we've got to order those things. H prime, and H double prime. Well, what do you think? Well, f of x is 0 at b. So H prime is 0. Now let's look at the other two. H is the integral from 0 to b. H of x, or H of b, is the integral from 0 to b of the function. So that is all of this area. So because it says from 0 to b and it's above the x-axis, we know that that is greater than 0. So I think we got a theme going on here. H double prime is the derivative at this point. Let's talk about what's going on with this function. This function is going down. So at b, the derivative of f would be negative because it is going down. So H double prime is less than 0. So therefore, in order from least to greatest, we would go H double prime is less than H prime is less than H. And it looks like that one is going to be right there in D, isn't it? Good. Awesome calculus discussion problem here. The f is a differentiable function, so the first important word there is differentiable function, such that f of 0 equals -4 and f of 5 is 5. Then which of the following must be true? So, you know, probably not a terrible idea to sketch that. F of 0 is -4, and f of 5 is 5. And it's differentiable, meaning it's continuous and no sharp points. And it's derivable the whole way. Good. Which of the following must be true? There exists a c from 0 to 5 where f of c is 0. Well, that seems pretty obvious. If it's differentiable, it's continuous. If it's continuous, there's no way for me not to go through 0 there. So that is definitely true. There exists d where from 0 to 5 where f prime of d is 0. Does the derivative have to equal 0? Well, I guess in the quick sketch I did there in 1, there would be no place where the derivative equals 0. Could it equal 0? You know, absolutely it could equal 0 a whole bunch of times. 1, 2, 3, 4 times in that sketch. But does it have to? It says must be true. I mean, it could, but it says must. So I would say that is not a must be true question. And then there exists a k where f prime of k is 9/5. What do they mean there? The slope somewhere has to be 9/5. What is the slope from here to here if we just did a straight line? It is up 9. If I count 1, 2, 3, 4, 5, 6, 7, and over 5. So the average slope is 9/5. Must there be a slope that equals that? And the answer is yes. There must be a slope that equals that because of the mean value theorem. At some point, if it's differentiable, and in this case it's probably twice, the actual slope must be equal to the average slope. And that's only if it's differentiable. It could be continuous, and that wouldn't have to be true. You could have a sharp point. That would never have that slope. But because it's differentiable, it has to be a smooth curve. Great. So these two are true, which is our old 1 and 3. All right, one more for this lesson. The limit, as h goes to 0, of e to the h plus 2 minus e squared over h is. Now, there's actually a few ways to solve this one. I could think of two good ones, but because it was discussion, because it is part of the new curriculum, when we have a 0 over 0, so if I were to put in e to the 0 plus 2 minus e squared over 0, I would get 0 over 0. And when I get that, I'm allowed to use L'Hopital's rule and take the derivative of the top and the derivative of the bottom and try that. So what's the derivative of e to the h plus 2 with respect to h? That will be e to the h plus 2. The derivative of e squared is 0, because that's just a constant, and the derivative of h is 1. So now, can I take my limit as h goes to 0? Sure. Now I can put the 0 in, and I'm left with e squared. D would be the right answer. So using that L'Hopital's rule, there's definitely a way to factor and talk about another special limit, which is totally doable and a good conversation to also have. Go Calc.